Good morning and welcome to part 4 of Statistics for Trauma Research. Today we're going to start talking about some statistical inference. Specifically, we'll talk about Z and T tests. There's a lot more than that, but I started putting this thing together and quickly got up to 50 slides, and I thought, let's just stop right there. Last time we talked about probability. Probability is just the likelihood that an event is going to occur, and it ranges from 0 to 1. 0, it means it's definitely not going to happen. 1 means it definitely will happen. Most things happen somewhere in between those. We talked about mutually exclusive, where we use the additive rule, and conditionally dependent events, where you can use the multiplicative rule to look at whether one thing and another will happen. Talked about the definitions of sensitivity and specificity with screening tests, along with positive and negative predictive value. The binomial distribution is just when you have two possible outcomes. There's the number of possible combinations times the probability of each combination happening. And talked about the binomial distribution a little bit more, that when it gets big enough, it approximates the normal distribution, and really got into the normal distribution. Normal distribution is going to be important for most of the statistical tests that we're going to use. So it's good to have a basic understanding of that. And the central limit theorem specifically really comes in handy because instead of using the standard deviation, we're using the standard error, which incorporates the sample size. Okay, so when do we get to the good part? Right now. You are lucky. You happen to be here. But more pertinently, since, as I mentioned, variability is part of statistics, how do we know when we see that one thing is larger than another, when we see a difference between two observations? How do we know if it's real? Since we know that there is some variation, and how do we take that variability into account and say whether that variability is just due to chance or whether it's finding that signal out of the noise and finding a real difference? So that's where we get to inferential statistics. What we were doing before was basically all descriptive statistics, talking about means and medians and distributions. This is inferential statistics is when you can get to the why, the hypothesis testing and figuring out why things happen, looking for connections between risk factors and outcomes. This is used to determine the probability that a conclusion based on analysis of data from the sample actually is true. The biggest hurdle to get over in statistics is choosing the right test to use. And it's going to depend on a number of factors, including what kind of variables you have, what's the dependent variable. Remember, the dependent variable is the outcome variable, whether it's continuous, ordinal, or categorical. You may have different types of tests that would be better to use. The number of groups that you're comparing, it could be just one group that you're comparing to a standard, or two independent groups, or two matched groups, or more than two groups. And I mentioned whether the groups are independent or dependent, and how big your sample size is. Those are all going to come into play when you're selecting your statistical test. One thing about statistics and statisticians, you'd think something that uses math a lot would be logical. Not necessarily the case in terms of how we name our statistical tests. We have things like chi-square and Mann-Whitney-U and Kruskal-Wallis that really don't describe what they do. But we'll get into those. Wilcoxon puts his name on a number of things. ANOVA, once you understand what that actually means, starts to make sense. But most of these you just kind of have to remember. For today, we're really going to talk about just this square right here, where we're looking at the T and Z tests. But there's a number of questions we can answer with inferential statistics. If we have a continuous outcome variable, we can look at a mean value in our study sample and decide if it's significantly different from some standard variable, standard value. So say if there's a national estimate of blood pressure or something like that, we can compare our sample to that and make some judgment about whether it's statistically significantly different than that. Whether the mean value in the study population changes over time, so you're comparing the same group at time 1 and time 2. There's a slightly different method to that, but very similar. Whether the mean value in one group is different from another group. So those are independent groups. So the example here is the mean systolic blood pressure in penetrating injuries significantly different from systolic blood pressure in blunt injuries. And yeah, you can even throw in 3 or more groups, and that's just going to tell you whether there's a difference in there somewhere. So is admission systolic blood pressure different for different mechanisms of injury? And there's more questions. You can go nuts with this. Dichotomous variables is when there's just 2 possible outcomes. So is the proportion with an outcome in the study sample significantly different from some hypothesized proportion, very similar to that mean example? So is the proportion with a positive head CT significantly different from a national study, maybe from an NTDB study? Is the proportion in one group significantly different from the proportion in another group? So again, that's the 2 independent samples, and you want to see if the positive head CT rates are significantly different for motor vehicle crash versus falls or something like that. And you can get into 2 or more groups and many discrete outcomes, where we're going to get into the chi-square test of independence next time, not today. So there are 2 strategies for testing and deciding whether you have a difference between 2 observations. You can do confidence intervals, and I'll talk about those briefly. But we're going to spend a little bit more time on hypothesis testing, where we're generating what's called p-values. The 95% confidence interval, and you've probably all seen examples of that in peer-reviewed literature, or you may have calculated some yourself. It's just a range of values that we're 95% confident actually contains the true parameter based on the data that we have. So remember, when we talked about the normal distribution, we discussed that just over 95% of observations occur within 2 standard deviations of the mean. So we can use that, assuming that our values are normally distributed. We can say, okay, about 95% are going to be within 2 standard deviations, and actually for the standard for the standard normal distribution, that number is 1.96. If you want to get precise about it, is going to be what we're going to use for the 95% confidence interval. There's a guy named William Gossett. He worked for Guinness Brewery, and Guinness did not allow him to publish. So he had to publish under a pseudonym. He used the pseudonym Student. And what he found was that as the sample size changes, that the shape of the normal distribution changes too. This becomes important when we're looking at both the calculating confidence intervals and hypothesis tests if we have especially small sample sizes. So we can see as the sample size goes down, this is with what's called the student's t-distribution with 3 degrees of freedom. So there would be 4 observations on that. It gets shorter and wider. And as it gets larger and larger, it approaches that z, that normal distribution. And when you get up to about 30 observations or so, there's very little difference between the student's t-distribution and the normal distribution. But it's important to keep in mind, especially when you have smaller sample sizes, that you may be using a distribution that's a little bit different. That's why for continuous outcomes, generally, the test we use is called a t-test instead of a z-test, because it works for all sample sizes. This is just an example of some confidence intervals I put together for a study I did a while ago on drivers who were killed in motor vehicle crashes so that the age of the driver according to whether they tested positive for alcohol or meth, or both alcohol and meth, or neither. And we can see that those that did not test positive for either meth or alcohol, the average age was 45.4, and here's our 95% confidence interval there. And the others were right around 33, 34 if they're positive for alcohol or meth. And we can see the size of that confidence interval here, not even coming close to the overall confidence interval there. Important, though, to keep in mind what a confidence interval is. It's not 95% of observations. It is the range of values that you're 95% sure the true mean is. Certainly, the drivers who died who were not positive for either were not all 45. They had ages ranging all over the place. But that was the average overall, and because it was a much larger sample size, you have a much narrower confidence interval there. So to get to the actual confidence interval, there's two components of calculating that. There's a point estimate, that's the mean, and a margin of error. The margin of error itself has two components. There's that z value for the 95% confidence interval. Remember, about just over 95% of observations are within 2 standard deviations of the mean. So for a standard normal distribution, it's actually, this z is equal to 1.96. And then multiply that by the standard error of the values that you saw. And so we can see as we change our level of confidence, so with the width of the confidence interval changes itself. So 80% confidence interval, we see a relatively narrow confidence interval. This is with a sample size of 50, mean of 40, and standard deviation of 20. It can be anything. This is just hypothetical data. And as we go from that up to a 95% confidence interval, you see it getting somewhat wider, and 0.9% confidence interval, it's a lot wider. And so we can say as we get more, as we want to be more confident, we're going to hedge our bets more, so that confidence interval is going to get a lot bigger. It's kind of like playing darts. If I'm shooting for the bullseye, I'm probably about 75% confident that I can actually get it within the triple ring here, but I'm probably 90% confident to 95% confident that I can actually get it on the board somewhere. So that width gets wider as my confidence gets bigger, and as I've had more beers. Okay. And these are just the different critical values of z for different levels of confidence. You get the reverse as your sample size goes up. Remember that standard error is the standard deviation divided by the square root of the sample size. So that's going to make this the confidence interval get much more precise as you have a larger sample size. So say same type of setup that we had before, the mean of 40, standard deviation of 20, only now we're just doing the 95% confidence interval. If we have only 5, we get a very wide confidence interval covering about 18 units in either direction, and you see that dropping dramatically as you get larger and larger. So when you get a large sample size, you're very confident in your results. All right. So, but we were going to talk about hypothesis testing and inferential statistics. But whenever we do that, we talk about the null hypothesis and the alternative hypothesis. And I apologize if this seems very, very basic. I have kids, so it's good to have characters whenever possible with them. So, I'm talking about Dr. Null and Dr. Alternative. They fight a lot. Dr. Null is extremely jealous of Dr. Alternative because even though Null is usually right, Alternative gets all the glory and all the publications because nobody publishes null findings, he thinks. Anyway, so Dr. Null says that The average systolic blood pressure for all trauma patients discharged last year is 120 because that's the national average, or it's normal blood pressure. And so he thinks, I think it's 120. Dr. Alternative says, no, I bet you're wrong. And he's not going to say whether it's higher or lower. He's just going to say Dr. Null's wrong because he likes to be contradictory. and so he says, I will take that bet and I will pay off even if there's a 5% chance that that you could possibly be right on that, because I think you're that wrong. So this symbol H0 or H0 is the symbol for the null hypothesis. Null hypothesis here is that systolic blood pressure is 120 versus the alternative hypothesis that systolic blood pressure is not equal to 120. So how are we going to settle that? Well, one way to go is to actually calculate that confidence interval. And the way to do that is, well, we need to know the sample size. So we had 2,650 patients discharged last year. Their mean systolic blood pressure was 136.7 with a standard deviation of 24.1. Our confidence interval is going to be our point estimate, so that's the sample mean here, plus or minus the z. This is big enough that we can use the z distribution, and that's going to be 1.96 times the standard error of the mean. So that's just the standard deviation divided by the square root of the sample size. Once we do all of that, we end up with a 95% confidence interval of our mean systolic blood pressure, ranging from 135.8 to 137.6. We can say based on that since 120 is not in that confidence interval, there's not even a 5% chance that it's there. So we can say with 95% confidence that the mean systolic blood pressure of our patients was not 120. That's really all we can say based on that. So going back, the actual equation for the confidence interval again is essentially point estimate plus or minus z times the standard error. However, like I was mentioning before with the t distribution, if we have a smaller sample size, then we have to go to a t distribution on that. And I said table 1b, but I didn't give you a table 1b. But there's usually a table of critical values of z distribution, t distribution. These are readily available in any statistical text or online, and I can get you one if you like. Essentially, to find the critical value of t in here, you're going to need to know how many degrees of freedom. That's just a term we use for the number of values that it is free to take, and that happens to be the sample size minus 1 for a t distribution. Okay. The other way to test that hypothesis is to actually do what's called a hypothesis test and calculate a p-value. So the p-value is going to represent the exact significance of the data. So we can say the probability is less than 1 in 1,000 of seeing an outcome like this purely by chance. So we can calculate an estimate of the p-value to summarize the exact significance of the data. We can get an approximate value if we have a statistical table of z or t values. But with a statistical computing package like even Excel, but I like to use SPSS, we can get an exact value. One way of thinking of the p-value is it's the smallest level of alpha, and I don't think I got into what alpha is yet, but I will, where we will still reject the null hypothesis. Alpha is the probability of falsely rejecting that null hypothesis when you really shouldn't. And this is an output from SPSS, and this actually is called the one sample t-test. And when we're doing this, we can, this is systolic blood pressure on admission, and we can test it against any critical value. But I just put 0 here because by doing that, you can get a 95% confidence interval of the actual mean. And we see by doing that, I end up with a confidence interval ranging from 135.7 to 137.6, and which is about the same as what I calculated earlier by hand. But to perform the actual hypothesis test, there's essentially 5 steps to doing that. First off, you want to set up that null and research or alternative hypotheses and select alpha, or your probability of falsely rejecting that null hypothesis. It's also known as type 1 error. Figure out what test statistic you're going to use, whether that's Z or T or chi-square or ANOVA. Set up the decision rule. The decision rule is just how are you going to know whether to reject that null hypothesis. Compute the test statistic, draw a conclusion, summarize significance, publish, and get famous, and rich. Okay. Here's a little bit more of what I was talking about with that type 1 error and alpha and type 2 error. There are, well, I guess technically 4 possibilities here when you're reaching a conclusion for a statistical test. One is that you actually reject the null hypothesis when there really is no difference. Null hypothesis is true and you reject it. That's a mistake. It's called type 1 error. And we usually set the probability of type 1 error to 0.05. So you've got a 1 in 20 chance of falsely rejecting your null hypothesis. Another possibility is you don't reject your null hypothesis, and you really should not. So null hypothesis is true. So that's a correct conclusion. The other type of error is when you don't reject the null hypothesis. You say, okay, null hypothesis is true, but it really is false, and that's called type 2 error. Usually that's because you didn't have enough power to find the difference. By power, that's usually related to sample size. Usually it's because your sample size is too small. And the other term for type 2 error, you may see it described as is beta. Okay, so going back to our example, to actually test that hypothesis, we've got the null hypothesis that the mean is equal to some hypothesized mean. Alternative hypothesis, there are 3 possibilities. One, that the mean is greater than the hypothesized value. The other, that it's less than it, and finally that it's different. These 2, where you're specifying direction, are called one-tailed tests. And this one, where you don't specify whether it's higher or lower, is known as the two-tailed test. Usually, we actually just use the two-tailed test because it's more conservative and you're more confident in your outcomes. The equations here should look very similar, actually, to the equation for the confidence interval. Just using some really basic algebra, you're just switching places with the difference and that z value to get the value of z or t, depending on your sample size. Okay, so in our test about whether the mean blood pressure is 120. All we're doing is going through and calculating a z value, and our decision rule, because we've got such a large sample size, so we can use a standard normal distribution, is to reject it if z is greater than or equal to 1.96 or less than or equal to negative 1.96, because that's going to be the middle 95% of our possible values. And this actually ends up giving us an enormous z value. You usually don't see them a whole lot higher than about 3 or 4. But this one's pretty big. It's 35.7. And with the z value that large, we can reject the null hypothesis because 35.7 is larger than 1.96. And we have statistically significant evidence to show that blood pressure is different from 120. And we actually can calculate the value off of that. If I was actually to give you the actual p-value, the zeros would go all the way out here for this particular one. But usually we'll just say if it's highly significant, we'll say p is less than 0.0001, so there's less than 1 in 1,000 chance of seeing a result like this purely by chance alone. And and often with those statistical tables of z values, you will see for different levels of alpha the z values for those, and remember that alpha represents that smallest possible p-value that you would still reject the null hypothesis, and so we can use that to estimate what the actual p-value is if we don't have a computer program to calculate it for us. All right. Using that same one sample t-test function from SPSS, all I'm doing here is just putting 120 as the test value. That returns this value, so it returns the actual t-value with the number of degrees of freedom and significance. If you see significance 0.000, that's the p-value right there. And the 95% confidence interval of the difference, we can see that if there was no difference, if we accepted the null hypothesis, the lower value in this case would be less than 0. So we'd go from negative to positive on that. And that's pretty much it for that. We can also do hypothesis testing for proportions. And like I mentioned before when talking about the binomial distribution, if it's large enough, if you have a large enough sample size, that binomial distribution actually does approximate a standard normal distribution. So we can use the z-value for this. So we can use basically the same test that we used before. And the calculation is essentially the same. You've got on the numerator just the difference, and the denominator is that standard error. And it's that this is how you calculate a standard error, p naught times 1 minus p naught divided by n for a dichotomous distribution. The only assumption here is that the minimum expected value is at least 5 for if you were to calculate how many observations you would expect to see with that probability. And if any of those is less than 5, then we need to use what's called non-parametric tests, and we'll talk about that at a later time. Okay, so we're going back to Dr. Null and Dr. Alternative. He thinks that 25% of patients are going to test positive for alcohol. Dr. Alternative is saying, nah, I think it's different. So we had 2,628 patients with alcohol results. 832 of them reported alcohol. I need to update this slide. It was not smoking, it was alcohol. So that was 31.7%. We want to know if that's significantly different from 25%. And so, same exact deal, set up a null and alternative hypothesis. The test statistic is calculated this way, and decision rule is going to be to reject if z is greater than 1.96 or less than negative 1.96. And so going through this, calculating the difference and dividing by that standard error, we get a z-value of 7.34. Again, this is much larger than our critical value, so we're going to reject that null hypothesis. And so we can say with a lot of confidence that the proportion with positive alcohol toxicology is significantly different from 25%, at least in our hospital, especially on Saturday night. And again, even though this is a dichotomous variable, we can actually treat it as a continuous variable for the purpose of this test. But we have to code it as 0 or 1. So if you code positive result as 1 and negative as 0, then the average of all of those is going to work out to be the average. And so you can test that to, or the percentage. So we can put in our test value of 0.25 here. And we can see here's the 95% confidence interval ranging from, of the difference between 25% and 31%. So this is a 95% confidence interval of the difference. If we did not reject the null hypothesis, if we concluded that there was no difference, the lower one would be negative, higher one would be positive. And again, we see a very significant p-value there. All right. So now I felt sorry for Dr. Null. And so he starts talking about blood pressure for motor vehicle occupants and motorcyclists. And we see that okay, motor vehicle occupants have a mean blood pressure of 134.7. Motorcyclists have 137.7. So we figure, all right, let's test that hypothesis that there may actually be a difference there, or there might not. So this is where we're looking at two independent samples. And so this is called the independent samples t-test or z-test if you like. And the same exact idea. We set up the null hypothesis that the two means are equal. Alternative hypothesis, you can state it as one is less than the other, in which case that would be a one-tailed alternative hypothesis. But usually we'll just use the two-tailed alternative is just saying that they're different. In order to use the z-value, both of the sample sizes have to be greater than 30. If either of them is less than 30, we need to use the t-distribution. We're throwing in a little different thing here for our standard error, and that's this SP. That's just a pooled standard deviation, so it's basically a weighted average of the standard deviations. Obviously, I don't expect you guys to calculate that, but this is how you would if you wanted to. And you can see we're incorporating the sample sizes and the standard deviations for each group. And so the one with the bigger sample size gets more weight. And so it's essentially going to be in the middle between the two. So it's going to be the sample size average of the two, but it's going to be closer to the one with the larger sample size. All right, so in this case, motor vehicle occupants, we had 422 with a mean blood pressure of 134.7. Motorcyclists are 112, mean blood pressure is 137.7. Here's the standard deviations. And so we've got this test statistic. Again, we're going to reject if the z-value, absolute value, is greater than or equal to 1.96. And, another thing about this test is that it assumes that the variances are equal. In order to test that, we just take the ratio of the variances, and if it's essentially if it's between 0.5 and 2, we can say it passes the eyeball test for being essentially equal. This ratio is less than 2, so that we will say that those variances are equal. And with this one, though, we end up with a z-value of 1.13. That is less than our critical value of 1.96, so we do not reject the null hypothesis. And because 1.13 is less than 1.96, and so we don't have statistically significant evidence that blood pressure is different between those two. So we can basically say they're the same. Okay. Now, if we were to run this in SPSS, we have a very similar type of test. Again, we'll put the test variable up here as systolic blood pressure, but then we need to put a grouping variable where we're going to define which two groups we're comparing. I have a variable called new type where I have the mechanism of injury. And so I'm saying, okay, compare group 1 and group 2. Group 1 is motor vehicle occupants, group 2 is motorcyclists. And so we've got over here the sample size and mean and standard deviation for each of those groups. And this first part over here in the independent samples test looks to see whether those variances are equal. And this top row says equal variances assumed. And it has another significance. This is another p-value. This refers to the null hypothesis that the variances are equal. And actually, even though we looked and said, okay, based on our eyeball test, they're not that different, it actually didn't pass this test because it has a significant p-value here. So we're going to assume that they're not equal and look at the second row that says equal variance is not assumed. And we have a t-value and a significance, and we can see, all right, so this is the actual p-value for this, and it's going to be 0.17. So that's ends up being not significant. And again, we can see our 95% confidence interval of the difference. The lower end goes negative, higher end goes positive. So 0 is included in that. So we can say that that they are not statistically significantly different from each other. All right. Finally, I don't know if this is finally actually, the hypothesis test for the difference in two proportions. And the question here is whether the prevalence of positive alcohol toxicology is different in motor vehicle occupants compared to motorcyclists. And we can see that just about 23% of our motor vehicle occupants had a positive alcohol toxicology compared to just under 18% of motorcyclists. So overall, it was almost 22% of those two groups together. And again, these end up looking a little complicated at first glance. You can essentially break it down into the two parts. The numerator here is just going to be the difference between the two groups, between those proportions, and the denominator is always some kind of standard error. And if there are two independent groups, you're going to be factoring in their sample sizes here too. Again, I'm showing this to you so you know what it looks like, but I know you're not going to calculate this by hand. For this example, again, we can use the z-value because we have a large enough sample size on this, and we calculate this out to 1.19 z-value. So again, we don't reject that null hypothesis, and we can say, okay, motorcyclists are just as likely to test positive for alcohol as motor vehicle occupants, accounting for that variability. And here's how we would do that. Again, you can use that independent samples t-test for that. And again, we've got the mean here. Since this is coded as 0 and 1, 0 for no alcohol, 1 for a positive test, that mean ends up being the percentage that were positive. So we've got 22.9% positive for occupants and 17.7 for the motorcyclists. Our test for equality of variances is 0.01 is the p-value for that. So that's significant. So we're going to look at the one that does not assume equal variances and see that 95% confidence interval actually does include 0, and the p-value is 0.21. So again, it's not less than 0.05. So we don't reject that null hypothesis. All right. So that was essentially the beginning part of statistical inference, hypothesis testing. Essentially saying that for continuous outcomes and even for dichotomous outcomes, you can use the normal distribution to compare your outcomes. But just to sum up, statistical tests, what one you're going to use is going to depend on what type of outcome variable you have, the number of groups that you're comparing, and the sample size. Confidence interval, we talked about, that's just the range of values that represents a level of certainty for a population parameter. If you want to have a higher confidence level in your result, that confidence interval is going to be wider. If you have a larger sample size, the confidence interval is going to shrink. It's going to get smaller. And that's calculated just as a point estimate plus or minus some margin of error, which is some critical value, that z-value, times the standard error. and most of what we did looked at that z distribution because we have a pretty good large sample size, but a lot of times for continuous outcomes you're going to use the t distribution with the degrees of freedom calculated as n minus 1. Type 1 error, also known as alpha, is just the probability of falsely rejecting the null hypothesis. Type 2 error is also known as beta, probability of falsely accepting the null hypothesis. And next time, we're going to go into kind of the next step where we have more than two groups or more than two discrete values. So multiple discrete values is where we're going to be using the chi-square distribution. And if we're going to evaluate a continuous outcome with 3 or more groups, that's when we're going to use analysis of variance. And that's where just kind of taking that next step beyond the t-test. I think that's all I have.